Now on to the easier lessons. We are going to start with Chapter 8, Lesson 8.1, Cellular Energy. All you need to know here is understand energy as a concept. So what is the cell's energy? To understand energy in the cell, we're going to need to understand energy in general. So let's talk about thermodynamics. Energy is the ability to do work. Your body is always using energy because your body never truly shuts down. Now, the first rule of thermodynamics, as we are about to talk soon, is that energy cannot be created nor destroyed. It can only be changed from one form to the other. And energy can be used, but it's never truly destroyed. As you can see here, assembling or breaking macromolecules, so things like carbohydrates and such, either yields energy or uses up energy. Passive transport does not use energy. Active transport uses energy. And then DNA activity, of course, uses energy because your cell is doing work. Now on to thermodynamics. As I promised you, the first law is energy can be converted from one form to the other, but it cannot be created nor destroyed. Second law is energy cannot be converted without the loss of usable energy. What do we mean by that loss of usable energy? The loss of usable energy is energy that's out in the wild, per se. You cannot use it. Now, we'll talk about that soon enough. Let's focus on the first law. Here we have the energy stored in food. When you take the stored energy in food, your body turns it into chemical energy, which then your muscles are capable of turning into mechanical energy. Now, energy cannot be converted without the loss of usable energy. Remember how we said the energy is out in the wild? Well, if you might have heard of this in chemistry, but out in the wild here is talking about entropy. It's the amount of disorder in a system, or in our case, unusable energy. Remember from last semester where we talked about how we lose energy in metabolism, which is why creatures up the food chain, for example, like the owl, have less energy available than the plant. This is because of the second law. The insect converts the chemical energy into mechanical energy and such, but it does not convert it at a perfect rate. Therefore, there is energy lost as entropy, as heat. So in most ecosystems, the entropy here is the heat lost in metabolism. You cannot harvest the heat in the air per se, and then use that energy. Even as hot as it may be in Saudi Arabia, we cannot use the heat in the air for energy. Now onto the two kinds of organisms that you are going to see interact with energy. People who are autotrophs, people who make their own food. The two forms of autotrophs, photoautotrophs, the one we all know. Plants photosynthesis, we'll talk about it in lesson 8.2. Chemoautotrophs, which are things that use chemicals to make energy, but they still are making their own food. Now, heterotrophs are organisms such as me and you who eat other organisms by food. For food. This is an example of how an autotroph works. Takes the sun, outputs energy. Very simple. We'll go over it in lesson 8.2 more. And here is an example of a very, very simple food chain, where the sun leads to the autotroph making energy. A heterotroph primary consumer eats the autotroph. Then a secondary consumer, which is another heterotroph, eats the original heterotroph. Now, metabolism. Now, forget everything you know about metabolism, as in human metabolism or animal metabolism. We want to talk about it on a cellular level. Metabolism isn't you burning food for energy. It's every sort of chemical reaction that happens in a cell. When we have a series of them, of interconnected chemical reactions, we call it a metabolic pathway, something that repeats. And there are catabolic and anabolic pathways. What does a catabolic pathway mean, and what does an anabolic pathway mean? Catabolic pathway you can imagine is you having energy stored in a battery. We're gonna call this battery glucose. So glucose is basically 6 carbons connected to each other. Each bond here between the carbon atoms has energy. That bond right there is filled with energy. And this energy is trapped in the bond. So if you, let's say, break down these bonds, well, then it's gonna release energy. So that's exactly what a cell does in a catabolic pathway. They take, let's say, glucose and they break it from 6 carbon into 3 carbon and 3 carbon. And this is purely an example. This is not a necessarily true reaction. This is just for you to understand here. So that the bond that was here, this bond, is broken down. And we release the energy in this bond. So rather than being trapped in the bond, there is no more bond. Instead, we're going to have energy in the cell. The energy is now free. It's free-flying energy. And then the anabolic pathway, you'll also use this example. We'll take the 3 carbon and 3 carbon here. We'll take them down here. And we have the energy. So we are going to reconnect the bond. So we're going to take this energy and place it right back into the bond. And when we do that, the energy will be gone, but the energy will not be deleted. The energy is now stored. Now, if you were paying attention before, you're gonna notice something. You're gonna tell me, well, you cannot convert energy without losing some of it. So there is no way the same amount of energy released from this bond right here is the same one used to create this bond. There is some energy here that was lost as heat. And right here, you are very much correct. The cell is going to use energy from its own energy reserve to make up the lost energy here if it's reconnecting these bonds. But to simplify the example, I said that. So what you understand from here is that catabolic, breaking down, energy release. Anabolic, building up, energy usage. So you can think of it as catabolic is negative and anabolic is positive. Here are a few examples of anabolic and catabolic reactions. Let's go over number 1. Condensation reactions creating ester linkages that link X group and Y group. Condensation reaction creating linkages. We created bonds. Therefore, this is directly an anabolic reaction. ATP to AMP, which is breaking adenosine triphosphate to adenosine monophosphate. So we broke down 2 phosphate bonds. Therefore, we are releasing energy, catabolic. Muscle mass increase. You are using energy to build the muscles. You're building something. Therefore, anabolic. And such goes for every example. Now let's look at a cycle that you may recognize from before as the oxygen cycle, but not quite. Let us start from the plant, like we always do when we are studying anything. Step 1, photosynthesis. The plant is going to use water and carbon dioxide. Carbon dioxide presumed to be available in the air and water from the soil to make oxygen and glucose. This oxygen and glucose is then eaten by, let's say, a cow. The cow consumes the glucose and breathes in the oxygen from the air that the plant released. This cow will undergo cellular respiration, which is a heterotrophic reaction, and then it will release carbon dioxide and water. And the cycle continues. Now, you may say, okay, so autotrophs do photosynthesis, heterotrophs do cellular respiration, but that's not entirely true. The tree will do cellular respiration, but to keep it simple, we are going to say that the heterotrophs do it. But the tree itself will do it at certain times, so you cannot say autotrophs only do photosynthesis or only do chemosynthesis. That's not entirely true. Now, on to cellular energy. We mentioned energy here in the form of ATP. We are going to look at ATP, which is the main energy unit of the cell. Now, you may know other forms of energy, such as light energy, that comes from the sun, mechanical energy, like stretching your arm currently, thermal energy, such as heat coming from an oven, and chemical energy, such as, for example, what's a good example of chemical energy? A battery. Speaking of a battery, we're going to look into a battery later on. Now, look at this energy conversion chart. We've all seen this experience. Chemical energy, food, goes to a human can move his muscle. Battery powers flashlight. Gas powers car. Electricity powers a toaster. Of course, there is energy loss in all of these, but nonetheless, energy is converted. And the cell does the same exact thing, just on a molecular level. The chemical energy is stored in the cell in the form of ATP. ATP is adenosine triphosphate. Adenosine, you say? Adenosine is, yes, it is the nucleotide from the DNA A, where we have the A, T, and then the C and G. And yes, adenosine triphosphate, the adenosine here, this is a nucleotide. But then what is triphosphate? What does triphosphate add here? How can we store energy in DNA where it's meant to store information, not energy? Well, I'm glad you asked. So ATP is, as we already mentioned, it's a chemical energy storage deal. It is the main energy carrier of the cell, most abundant, you could say, and all organisms use it. Now the adenine group, then the ribose sugar, and then the phosphate. So adenine and ribose here, nothing special. We've already studied genetics in 8th grade. This is adenosine. And then we have the phosphate group. The phosphate group is what stores most of the energy. The phosphate bonds here between the phosphate group is where we actually get our energy from. We never break down for example, the bond between adenine and ribose. We don't touch this. So adenosine, the first part of adenosine triphosphate, is never going to change. It's always going to be A. And it's always going to have at least one phosphate group. So if you're still with me, then the least version of ATP is going to be adenosine, ribose, and one phosphate group, also known as adenosine monophosphate, or AMP. And then the second highest form of energy is going to be adenosine diphosphate. What does di mean in chemistry? It's ADP, and it's two phosphate groups. And then the greatest of them all, the one with the most energy, adenosine triphosphate, where you have 3 phosphate groups. Okay, but how does the energy in the phosphate groups matter? Well, it matters when you look at the ATP-ADP cycle, where we're going to be removing and adding a phosphate group. So we take ATP and some water. Through a chemical reaction that's far too complex to explain currently, we are going to end up with 2 things. Energy, just energy, and a phosphate that's left alone. This energy is the same exact energy that was holding the phosphate together. It's the energy in this bond right here. And now we have adenosine diphosphate and a phosphate group and then energy. These are the products you could see. And the way the cell continues this cycle back and forth is how cellular energy is either stored or used. And that is all for lesson 8.1. Best of luck studying with the finals, and thank you.